if you have a line integral over a simple closed curve C over a vector field, which would be this, Green's theorem says that you can turn that into the double integral of the region enclosed by that curve C. And the reason we care about that is because this calculation is quite often a lot simpler and easier and quicker to do. So we have our vector field function. You can see in the green, the vectors go in different ways. We have our curve C, which is a vector valued function, vector R. And the line integral over a vector field, I'll put the derivation of that, of a video that I have on that in the description, but just real quickly. So what you're doing is you're dotting the field vectors and the curve vectors and taking the integral of that. So this is the conceptual formula. This is the calculation formula. This is typically what we use to take the line integral over a vector field, unless, of course, we're going to convert to this. And so here's our vector field. X and Y are typically called P and Q. And so we're dotting the vector field and the curve vectors. And so if here, it's just the same thing, it's just the vector field dotted with the derivative of the curve function. If we go ahead and dot those, we just get this, and you'll notice this is no longer a vector. It's just a function that's going to be integrated, and it's typically parametrized, but we could cross out the t's and just kind of get a shorthand notation for that here. So that's kind of the springboard for what we're doing here. The strategy for deriving Green's theorem is we're going to take an integral over a closed curve, but what we're going to do is we're going to ignore the y components. We're just going to pretend all the vectors were just nothing but horizontal. And then later we're going to do one with only the y component, all the y components of all the vectors. And then when we put the whole thing together, then nothing is left out. And we have all the components of all the vectors, and we have a complete integral of a vector field. But if we just look at the x component, we can do some cool things. So basically what we're doing is we're taking our integral, and instead of having a p and a q part, we're just going to do the p part. So instead of doing p dx, q dy, we're only doing p dx. And so basically this is this, and here we just have this, and there's no q component. Notice that that changes from a dot product to nothing but multiplication, because the first part of the dot product would be multiply the two x components, and that's what we have. So there's no dot product anymore, and we don't really need parameterization. Well, first let me mention this. So dr would be the same as dx. Logically, you could kind of think if you have the r vector and there's no y component, well then the r vector is nothing but the x vector. So a change in a change in r is the same as a change in x. Or if you wanted to see it explicitly, so the differential, a change in r, would be dx dt times dt plus dy dt times dt, but we are not doing a y component here. So that just means that this is equal to this, and then if we're not parameterizing, we just get dr equals dx. So we just change this to dx. And so now this is what we have. This is what we're going to use to do this first integral. But since the situation has changed to rather than being parameterized, we're basically doing a couple of functions. We're going to have to split this curve into two parts. It's going to have to be two functions because it wouldn't be a function if we did one continuous one. And so basically we take this, put it here, and we do one integral for this. So basically we're calling this line y1 of x and this line y2 of x. And so we're getting an integral from here and then getting in this integral from here. Notice the bounds of integration are switched because these things have direction. And so we're doing the integral from a to b of y1 of x, and then we're coming the other way, which means we have to switch the a and the b. Okay, so that gets us up to here. And as far as the parameterization, just to elaborate real quickly why we don't really need it. If we took this and parameterized it, so we could say, well, we'll make x equal t, and then y will be a function of t, rather than x and a function of x. And then if x equals t, well, then dx dt would be 1, so dx is the same as dt. So if we plugged that in to here, then we'd have this. We'd have dt instead of dx, and t instead of y, and g1 of t instead of y1 of x. But then when we think about, well, what are we doing here? Why don't we just go back to x and y of x and dx, because that's what we were doing anyway. The parameterization isn't really helping in this case, since we changed from a full line integral to only in the x direction. Okay, so maybe that was too much of an explanation, I don't know. But anyway, so basically we're starting with this. It has to be two parts because we need two functions. We saw that already. And now from here to here, all we're doing is switching a and b to be on top to match this, which means we have to make that negative. And then this is just taking this and turning it into a single integral, which is exactly why we made this match this anyway. And between here and here, nothing has been done other than put a negative in front of here and switch these two. And that's just to kind of pattern match to the formula that is where we're going. Since we know we want it to look a certain way, you'll see what I mean later. So that's just kind of a manipulative move that we're doing. Now, to get from here, so this is our goal. To get from here to here, if you think about this, okay, this is this. And it helps to think backwards probably. If you had this means nothing more than you have a function, and notice that instead of these, we just have a generic y, because the y2 of x and y1 of x have been put up here. So if I take this function and input this, and then take it and then subtract another copy of this with this put in here, well, that's exactly what this means. So hopefully it makes sense that just this part is logically the same as this. It's just two different ways of writing the same thing. Now we just have one step left. We have to get from here to here, and we have the x part done. Well, so let's think about just this and this. So think about if I took this thing and I took the derivative with respect to y, here we go, and then I took the integral with respect to y, I'm doing the exact opposite of what I just did, and by the fundamental theorem of calculus, this has to equal this. Because if I have this, and I take the derivative with respect to y, and then I plug this in and make another copy and plug this in and subtract them. Well, that's exactly what I have here, which is exactly what we have here. So that gets us to here from here. And that's what we wanted. So our line integral, our general line integral, when only taken with regard to the x component, just becomes this, which is this. And then we get to this. And there we go. So we've got the first part done. So just to sum up, this equals this, which is exactly what we have here. Now we need to do no x component. So this is what we just derived. So we have the same curve, and we're thinking only of the y component of all the vectors now. So we need to think of two curves that pass the horizontal line test that comprise our original curve C. And so we have x in terms of y now, so that they pass the horizontal line test. And now we're going to do all the same stuff. Our general formula turns into this when there's only the y component. And so from these two curves, we get these two integrals. And then we want to switch a and b, so we put the negative in front of it, which allows us to get one integral now. Now this is where last time, so we could pattern match to Green's theorem, we wanted the negative in front of the one with partial p partial y. We're not going to do that here. So we can ignore that step. And from here we get to here, which is through the same reasoning as we just did. And then from here to here, and we basically get this. And now we've done both halves of the derivation. The only thing left to do is take what we've derived and add the two equations. So when we add the left side, we get this. We add the right side, we get this. And that is Green's theorem. I'll close with a quick example of taking the line integral of the unit circle. So that's our curve C over vector field. This is the vector field, so F is of course PQ, and P is Y, Q is Y squared. And this is our curve, this is the unit circle as a vector valued function. So we're going from 0 to 2 pi. We're going clockwise. Okay, now if we didn't have this, which is the advantage Green's theorem gives us, we would just use the standard formula of the line integral over a vector field, which would be the dot product. So the two x components plus multiplied plus the two y components. And so the way we would do it, this is the computational formula for this. And this is a conceptual formula for this. So this, and this are the same thing. Okay, now to do this, this is the input to the vector field. If you're not familiar with line integrals over a vector field, I have in the description my derivation of that formula. So you might want to watch that first if you feel the need to. So what we would do is once we input R into F, we get this. Notice it's just the y's. So this becomes sine and then sine squared. And this is our prime of t. So we just take the derivatives of those, and that's what these are. And now we have our two vectors that we're ready to dot. So here they've already been dotted. Now we no longer have vectors. We just have an expression to take the integral of. And I'm not going to dwell on this very much. I'm assuming that you know how to do integrals. but basically we can split this and this into two separate integrals. And then I use the double angle identity to get rid of the sine squared and get this. And for this, you can make sine of tu and do a u substitution. The cosines cancel out, and you just get u squared from 0 to 0. Now, this is going to go to 0. So this is gone anyway. That just leaves this part for this. So it when we take the integrals of both of these, we get this. When you plug in your 0 and 2 pi, this goes to 0 anyway. So it really just leaves this, which is this, which is this. So we get negative pi with all this. And this can be a considerable amount of work to do all this integration. Method 2, okay, again, thinking of our unit circle. And all we need to do the Green's theorem formula here is just take partial q partial x and partial q or partial p partial y. And so this is q, so the partial of q with respect to x is 0 and p is y, and we get 1. So we basically get the double integral of 0 minus 1. And now we move that 1 out in front. And in this case, which is a little simpler than a lot of cases, sometimes you might have bounds of integration that you actually have to do. But in this case, we can notice that if we put a 1 here, this is nothing more than an area, and our shape is the unit circle. So really, we can just use geometry here. So we get negative 1 times the area of the unit circle, which has a radius of 1. So basically, we just get that. We get negative pi. So as you can see, we got negative pi for both of these, but this was a much easier way to go.